Okay, hello everyone. Welcome back to these tutorials on the theory of computation. So today's video is going to be about, well, one of today's videos is going to be about determining what the language generated by a context-free grammar is. So far what we've done is we've designed grammars to generate, particularly we've designed context-free grammars to generate languages. Now we're going to try to do the opposite, where we're given a grammar and we want to know what the language generated by the grammar is. Okay, so in this particular case, um, we're going to want to determine the language generated by this grammar. Oops, by, oh, if my laser pointer could work. I see my pen is not working. So the grammar is, the start variable s gives you AS, BA, ABA. And then we have a second variable here where A gives you either A, ABB, or A, AB, or A epsilon. Okay. So clearly, the first thing we can already notice is what we're going to assume. We're firstly going to assume that S is the start variable. This is a safe assumption to make. Um, if you're given a grammar and you're only given the production rules, you can always really safely assume that X is the start variable. So the first thing that sort of comes to at least my mind is it looks like the only um, production rule that has only terminals on the right-hand side. So the actual production rule that's going to allow you to finally generate at the end of the sequence of derivations strings of terminals. The only one is this one, right? So I have to somehow see what the general process is to get from S to A and then from A generating epsilon, because that's really the only way that I'm going to be able to generate strings of just terminals in this grammar, right? So, so I kind of want to see what strings are generated along the way from S going to A and then trying to finish my production rows with just this epsilon here. Okay, so let's look at this a bit more carefully. I know that I always have to start at my start variable. So what I'm going to do here is I'm going to say, well, what are my options, right? When I start at S, what are the options I have? Well, I can decide to remain in this sort of DFA intuition context, remain at this start variable S by just generating a bunch of A's here on the left, right? So I can generate one A, then I can replace this S again by AS, and I get AAS, and again, so I can get AAAS, and so on, right? And so what this tells me is I can generate any number of A's on the left-hand side of S, right? On the left of S. Okay, so this is, I'm sort of abusing notation and I'm using a regular expression here, but you get that this means that, I can start at S, I can decide not to generate any A's, or I can generate any number of A's that I want. Okay, so that's the first thing I notice. But remember, at some point, I do need to go from S to A if I want to start being able to generate just complete strings of terminals, right? Because this is the only production rule that actually doesn't generate an additional variable and only has, non-variables, right? So namely terminals, or in this case, the empty string, right? So how can I get from S to A, right? So the other option, instead of saying generate a bunch of A's, is I can directly go to the variable A, right? By either generating on the left-hand side BA, or, right, by generating ABA, right? So what that tells me is that if I sort of take these two cases together, I see that S can, first of all, generate any number of A's, right? And then S can either go to A using, so I'm going to keep this A star here, but using either BA or ABA, right? And so here you're noticing that I'm using sort of production rules with regular expressions. This is a heavy abuse of notation, which is fine just for like problem solving, but just be aware that this is definitely not anything valid. Like this is not a valid regular expression, and this is not a valid um, it's not a valid sort of sentential form in context-free grammars. You do typically need to sort of write things out just as strings, not with like more shorthands like these guys. Okay. But I think just intuitively, this probably makes sense, right? Because like if I start at the start variable s, if I start at the start variable s, I can either go to A with only a BA or an ABA at the left, or I can have to the left of those guys a bunch of A's, right? So this is what it's telling me. This is like the structure of the string so far. Now, what happens then when I get to A, right? So when I get to A, right, then there are two options. Well, there's of course the option of just sort of stopping with the empty string. But let's consider the two other interesting options, right? So you can either use this rule or use this rule. Okay, so what does the first rule tell you? The first rule tells you that for every one A on the left, you generate two B's on the right, right? And what does this guy tell you? This guy tells you that for every one A on the left, I generate one B on the right. So what this kind of makes me think of is I kind of have a lower bound and an upper bound on the number of B's I can have based on the number of A's, right? So at least I have to have as many B's as A's, right? So when I sort of use either of these production rules, I have to have at least one B here, right? So the number of B's that I generate, the number of B's I generate has to be at least as great as, has to be at least as equal to, has to be greater than or equal to A, right? And at most, right, so that would look like, something like ABV and so on, right? And then I can finally use the sort of empty string production rule here, and I can get something like ANBN, right? Or at most, what can happen is for every A that I see, I can use the other rule, like I can use the BB rule, right? So for every A, I generate two B's, and I do this again. So now I have four B's on the right. And you can see that if I continuously use this, I'm just going to sort of augment my number of A's by one and augment my number of B's by two, right? So eventually what's going to happen is I'm going to get something that looks like AN B2N, okay? And so actually, it turns out that in this form, right, with these two rules, I can get something like, so I can get something like, A can, in some number of steps, derive something like A6, B6, and it can definitely derive the sort of upper bound, which is whoops, A6, oopsies, A6, B12, right? So that's the sort of n and 2n. But it turns out I can also derive anything in between, right? So anything like I can derive A6, B7. Why is this true? Because, what does A6, B7 require? It requires me to sort of generate, to use this production rule 5 times, right? Because then I get 5 B's and then plus this production rule only once, right? And so in total, I use it 6 times. And what I get as a result in terms of the number of B's is 5 B's plus 2 B's. So that gives me 7 B's. Okay. Sorry, someone was looking at me. Okay. So that's, like A6, B7. And I can also get something like A6, B11 and anything in between. I'm not going to prove that to you, but you can just try to think and see why you can get any number in between n and 2n. Like for instance, in this almost extreme case, you can say, well, I can use this production rule once, so I get 1b, plus I use this production rule 5 times, right? So I get, 5 times 2, 10, 5 times 2, so 10 B's plus 1 B, so 11 B's, right? And I mean, you can kind of see, like, if I use this 4 times and this once and this twice, sorry, then I get 4 plus 4, so 8 B's. And so you can see that it goes sort of in increments, and you can like sort of reach every single value there from 6 to 12, okay? So what that tells me in general is, in general, um, A can generate something like AN bk, right, in any number of steps, in some number of steps, where k is between n and 2n, okay? So that's what A can generate, right? Because at the end, of course, at the end, what I'm assuming, I'm implicitly assuming that at the end, I'm just using this A gives you epsilon transition, right? So like for something like this, the last rule you would have is something like AN, A, BN, and then you would finally replace this with AN, BN, right? That's what I'm assuming. So that's how you use the final production rule to finally get just a sequence of terminals rather than, terminals and variables. Okay. So what does that mean like altogether, right? Altogether, that means that, from S in some number of steps, I can get A star, and then we said BA or ABA, and then I get to A, right? And then A in any number of steps, I can generate this guy, right? This guy. So then really what that means, if I just copy this by writing it very quickly, is I get this and then concat, right? Something that looks like an bk, where k is between n and 2n. So this is definitely not valid notation. So really the best way to write this out is using something like set builder notation. So you could use something like L of G, right? The language generated by G. Remember, that's the set of all terminals that, set of all strings of terminals that you can get at starting from the start variable S. So what is that? Well, I can actually use the regular expression notation for the first part. Um, and then I can just use like a set builder notation for the second part, right? So concat, so now this becomes the language concatenation. So you're concatenating every single string in here with every single string in this guy, where this latter guy is going to be A and BK, where um, so n starts at, n can technically be 0, right? Because you can, from A, just derive the empty string. So n can start at 0. So I'm going to say n is in the natural numbers because in computer science, 0 is included in there. And then k, the range of k is that it's between n and 2n. Okay? And that's the language generated by the grammar G. So I'm not going to give you a proof of correctness, but in this case, actually what the proof of correctness would entail is you would have to make like a claim about what are the strings generated by S, and then what are the strings generated by A. So make that claim, and then prove both of those claims sort of by induction, and sort of combine them to show that altogether the language generated by the grammar is what I just said here. So the one note that I would like to mention, so note, is notice that when I was doing the sort of derivation for this set of production rules, I was kind of thinking about it in terms of a DFA or like a DFA or an FA. And that's not really a coincidence. It's because here the set of production rules are all of the form what we call right linear. So these are right linear production rules. Okay. And it turns out that there's a one-to-one mapping. So you can think of it as a bijection between a DFA and a corresponding right linear production sort of conversion, right? So like for instance, um, you can think of S as like your start variable, right? So S could be the start state, sorry. Um, and then what does AS mean? AS means that you sort of have a self loop on S with A. Uh, then BAA, that would be something like, you have a B, then you have some intermediate states, then an A, and then you go to state A, right? That's one way of getting to A. Another way might be by reading an A and by reading a B, and then by reading an A, right? So then I get something that looks like an NFA, and then I can sort of convert it to a DFA. Um, And so that tells me that, and so this rule applies in general to any grammars that only, right? They must only have right linear productions. So as soon as you introduce something that's not right linear, so right linear production rules are of the form um, sort of some some string from the alphabet, so some string W. Whoops. So right linear production rules look like something like A gives you a string and then B, where B is a single variable, A is a single variable, and then W is just um, some string of terminals, right? So the reason why it's called right linear, linear just refers to the fact that there's only one variable on the right, and right linear is because the variable is at the rightmost part of the production rule. So you can't have like W and then some other string here. Okay, so it has to be at the rightmost part. Um, so yeah, I was just saying that you can take something like this and convert it to an FA like this, and then convert the FA to a DFA. And then similarly, if you had a DFA, something like this, okay, then you can convert this to a right linear grammar. How? Just say that Q0 and QF are variables in your grammar. Then Q0 from 0, you can go back to Q0, and reading a 1, you can go to QF. And then from QF, reading a 0, you can stay at QF. But like reading now means generating in the context of the grammar. And then here, if this is a 1, then QF also has the production rule 1 QF. And then finally, because this guy is an accept state, then I also want to include something like the empty string, right? So then if I accept something like 0, 0, 1, right, that's accepted by my DFA, 0, 0, 1 is accepted by my DFA, then I can sort of simulate the acceptance by generating, right? So I can say, Q naught gives you 0 Q naught, then replace the Q naught by 0 Q naught again, and then replace the Q naught by 1 QF, and then just replace the QF by the epsilon, right? And that just gives you 0, 0, 1. So you can see that there's this sort of one-to-one mapping. And the reason why I bring this up is because this is probably going to be useful in one of your assignment questions. I won't tell you which one.